Okay, hi group. This video lesson is going to be focusing on two worksheets. Student worksheet 10.4a is just a straight gas stoichiometry exercise. This is mostly going to be looking at stoichiometric calculations converting moles to liters, potentially to mass as well if required. And I want to just do a little bit of review through this video as well on some topics that have been found in separate chapters and now we're pulling together. And there's another worksheet in this video lesson which we're going to look at, which is called Mixed Stoichiometry 10.4c. This is more a real variety of questions which involve solutions, just strictly gas phase reactions, and some that have kind of mixture of different states. So I think to start with, we'll look at what we understand about stoichiometry. There's a lot of different relationships that need to be drawn on, but at the core of stoichiometry, it's looking at measured values, how those relate to the amount of a particular reactant or product in moles, applying a mole ratio between reactants, between products, and finally converting that back to a requested or required quantity. The gas phase reactions that we've been looking at so far involve relationships with volumes of gases at standard temperature and pressure, or standard ambient temperature and pressure. If we go back and we look at the summary of Gay-Lussac's law of combining volumes and Avogadro's theory, there's some really good information in here that will help us with gas stoichiometry. We need to understand that gases, when they do react, they combine in whole number ratios by volume. Gases, when they react, do so because, as Avogadro's theory states, at the same temperature and pressure, a volume of one gas and an equal volume of the other contain the same number of particles. So because of that, in other words, the same number of moles, we can use these whole number ratios, such as the production of the ammonia, almost in place of mole ratios. Again, we don't want to reinforce any misconceptions here, so we're not saying that 1 mole is equivalent to 1 liter, but if we want to compare by moles, we can, using the coefficients, or we can compare by liters because of Gay-Lussac's law of combining volumes. So it's whole number by liter, whole number by mole. Finally, we have the molar volume of gases, which are constants which we can use in reaction equations when we want to relate moles to liters. We go back here to this stoichiometric calculation summary. So we know that we've got our 22.4 liters per mole under standard temperature and pressure, so that's 0 degrees Celsius, and 101.325 kilopascals. We have at standard ambient temperature and pressure 24.8 liters of gas for every mole of gas, and that's under 20 degrees Celsius and 100 kilopascals of pressure. We have relationships between, of course, mass and moles, which we've used previously. We also have relationships between number of particles and number of moles. Okay, when we get into the mixed stoichiometric calculations, we're going to need to also draw on some of our skills working with solutions, and that'll come later. So solids, gases, primarily we can rely on these relationships that are shown on the screen before you. And when it comes to looking at solutions, we can go back and deal with that separately. So let's look at the general process here. Is for a particular question, start with a balanced reaction equation, and then convert our measured or provided quantity, apply a mole ratio, and then convert our final molar amount into a required quantity. So in the first example we have here, the industrial manufacture of sulfuric acid, which is aqueous hydrogen sulfate. In this case, requires the complete combustion of octasulfur. So octasulfur is S8 molecule. This is a solid, and here we're trying to get sulfuric acid in the industrial process, but the particular chemical reaction we're looking at appears to just involve the combustion of octosulfur into sulfur dioxide. So here we have 8 SO2 and 8 O2. So it'd be a 1:8 ratio by moles. Now in this case, our product is a gas. One of our reactants is a gas. So we have to be careful when we look at reactants as a pair that we don't apply mole ratios to those, because only one of them is a gas. So what mass of octosulfur is required to produce 112 liters of sulfur dioxide at STP? So we have our volume here, which is 112 liters. Now what we can do with that, since it's at standard temperature and pressure, is we can convert that into a number of moles. So the number of moles here would be equal to the volume of the gas multiplied by the ratio of 1 mole for every 22.4 liters. Okay, at this point we'll pause and I'll fill in a little bit more of the solution here. You can kind of plan out what the next steps would be for this to get our final amount, which would be the mass of our reactant. Okay, so the number of moles of the product gas is 5.00. The mole ratio between sulfur dioxide and octosulfur is 8:1. So moles of octosulfur will be moles of sulfur dioxide divided by 8 gives us 0.625, and I just multiply that by the molar mass of octosulfur, which is 8 times the molar mass of a sulfur atom. So I get 160 grams. I guess to 3 decimal places, or 3 significant digits, that would be 1.60 multiplied by 10 to the 2 grams. So that's our final answer for number 1. Okay, so this is an incomplete combustion reaction. So in this case, oxygen is the limiting reagent, and the coal or carbon solid would be the excess reagent. So we're still going to get common oxides in this case, which for carbon, the less common oxide would be carbon monoxide. So that's the valence reaction equation. Making that balance would just require a simple adjustment here. So now that we have that, we can look at the number of moles of coal which are being reacted. In this case, this would be mass divided by molar mass, and I'll take this as 1.50 times 10 to the 6 grams. Actually, correction, that would be 5, because there are 1,000 grams in a kilogram, and I have 150 kilograms, so I have 150,000 grams, and 100 thousands is 10 to the 5. Okay, so that's the number of grams. Divide that by the molar mass of carbon at 12.01 grams per mole, and this will give me my, okay, so I get approximately 12,490 moles. So to the 3rd significant digit, that's 1.24. Carry the 9 times 10 to the 4 moles. This is related 1-to-1 with carbon monoxide. So the moles of carbon monoxide would be exactly equal to the moles of carbon. So that's, again, 1.249 times 10 to the 4 moles. And since this is a gas, I can relate this to a volume by looking at the conditions, standard ambient temperature and pressure. So the volume would be equal to that amount multiplied by 24.8 liters for every mole. For 1 mole. So we have equal volumes of gas at the same temperature and pressure contain equal number of particles. And we have the fact that whether it's a mole of carbon monoxide or a mole of oxygen or a mole of ammonia, at standard ambient temperature and pressure, that gas would occupy 24.8 liters. So if we have 12,000 some moles, we just multiply that by 24.8. We get our final answer in liters, which is 309,742 approximately. So to the nearest third significant digit, I'm looking at 3.10 times 10 to the 5 liters. Okay, number 3. So this is the production of hydrogen gas. It's the only gas in the reaction equation here. That's standard temperature and pressure conditions. Here the other reactant is aqueous hydrogen sulfate again. So sulfuric acid in this case is needed for the reaction equation. So H2SO4 is its chemical formula. Here to balance this, have to remember that iron's most common ion charge is 3+. So in this single displacement reaction, iron displaces hydrogen. Hydrogen is kicked out as an element, and iron now bonds chemically with the sulfate, potentially to form a soluble or an insoluble product. We could check our solubility chart to verify that iron 3 sulfate has high solubility. I'm not sure about that, but at this point it's not relevant because we're just looking at the amount of gas produced. So to balance this reaction equation here, we have need of 3 sulfate groups on the left side, so let's make that a 3. Balanced sulfate as a group. We have now 3 hydrogen molecules that are being produced for every 3 molecules of sulfuric acid, and then we would need 2 atoms of iron. Okay, so in this case, we're starting out with a mass of iron, which is 10.0 grams. And here, just to plan out your strategy for this one, we're going to apply the same process as we did before. We're going to convert our measured value into moles. We're going to apply the mole ratio and convert that back into the requested quantity, which in this case would be a volume. So like number 2, we're going to be mass to moles to moles to mass. So calculating the number of moles of iron, Fe, would be 0.179. Mole ratio between iron and hydrogen is 2 to 3. Now what ends up being relevant here, although iron 3 sulfate is not a gaseous product, the formation of that affects the balanced reaction equation. So that was relevant because now we have 1.5 times as many moles of hydrogen formed as we start out with moles of iron, and in this case we would multiply by 3 and divide by 2, or multiply by 1.5 and then apply the 22.4 liters per 1 mole standard temperature and pressure molar volume to that amount. We get 6.02 liters. Alright, here our reaction equation once again. Sulfuric acid is involved. It's a really important chemical clearly from these examples, so we can take that here to mean that maybe sulfuric acid is reacting in its pure form to make the fertilizer. If we didn't want water around, we wouldn't want it to be aqueous. So since the fertilizers are spread in solid form, most of the time we would want a solid fertilizer, ammonium sulfate. So let's take sulfuric acid to be a liquid. Ammonia is a gas, and in this case, to balance that, look at the fact that ammonia is on the left side and ammonium on the right side. So it's not the same. One's a polyatomic ion, the other's a molecule. We have sulfate on both sides, however, so we can balance that as a group. And in this case, if we just double up the number of molecules of ammonia, that'll balance nitrogen, and it'll also balance hydrogen at 8 per side. So here, take note, the amount of ammonia is quite large. It's 75.0 kiloliters. So this is a volume, 75.0 kiloliters. So the measured quantity is a volume. And what we end up wanting to know is the mass of this. Now, since the conditions for this reaction are at 10 degrees Celsius and 110 kilopascals, we can't use standard temperature or standard ambient temperature and pressure because they don't match. So what we're going to have to do is use the ideal gas law, and in this case the ideal gas law will allow us to calculate a number of moles for a gas under a certain pressure, volume, temperature condition. So here, a number of moles of this gas for NH3 would be equal to the pressure volume product divided by the gas constant times its temperature. So we just need to do some conversions here before we move ahead. 10 degrees Celsius is 283 Kelvin. We have a pressure already provided that's given at 110 kilopascals, and we have our ideal gas constant, which is 8.31 kilopascals liter for every Kelvin mole. So that is all we need to calculate number of moles. So number of moles would be calculated at this point. Now 75.0 kiloliters is 75,000 liters. Tens of thousands are 10 to the 4 as a power. So that's 7.50 by 10 to the 4 liters. If we don't make that conversion, I'll just emphasize here, our final answer in moles ends up being in the thousands. And so it would have been easy just to leave it at kiloliters and end up with kilomoles without making any change to the number 75. But having done that, we end up with a much larger number of moles, which we can leave as is, or we can convert it back to the nearest unit up, which would be kilomoles. So that's the number of moles of ammonia. The number of moles of ammonia is double the number of moles of ammonium sulfate. So we'll make an adjustment here for our mole ratio. And the rest of the calculation is just crossing over to product side. Mole ratio is 1 to 2. So I get a new number of moles. I calculate the molar mass. Remember to show the work for calculating the molar mass. At least show that you've done some calculation if you don't actually have room to show the steps. There are 4 different elements there, and there's multiple atoms of most of them. So I double check that, and that final calculation into grams ends up being a really large number in the millions. So the nearest unit for 10 to the 6 would be mega. So the letter for that unit is capital M, representing millions, or 10 to the 6th power. Now before we look at solution stoichiometry mixed with gas stoichiometry, just a little bit of review here. Solution concentration is defined as the amount of solute in an amount of solution, and it's a ratio. So concentration, if something is very concentrated, it has, for a certain amount of solution, lots of solute. That's kind of visually shown here on the right. With a concentrated solution, and a dilute solution would have relatively few solute particles per solution amount. Concentration is an important unit because we can't visually look at something and necessarily determine if it's concentrated or dilute. We have to go with what's known to have been dissolved in the solvent. So here, although there are many types of concentration that we've looked at or will have looked at in this course, percent concentration is not applicable. Very low concentrations are also not applicable. The one we need to focus on is the mole per liter concentration, and again that one was related to the volume and concentration and moles by this formula here. So concentration is equal to moles of solute divided by volume of solution, and the unit for that is moles per liter. So we commonly remember this formula C equals N over V as N equals CV. Either are fine to use depending on what we're trying to solve for. Okay, from that, volume would be equal to moles divided by concentration. So the common formula that we're going to need to use is moles equals concentration times volume. When we go back here, this would be another linking relationship that would allow us to determine how many moles of reactant or product based on the concentration of the solution and the volume of the solution. Volume needs to be in liters, and concentration should be in moles per liter. Otherwise, as long as the volume units match, we're okay. Okay, so let's go back to this worksheet 10.4c. So mixed stoichiometry questions are going to involve mixed phases. Okay, so here the skeleton equation here for zinc reacting with aqueous hydrochloric acid is shown. To balance that, we need to know that zinc chloride is ZnCl2. If we balance chlorine, we would have also balance hydrogen, and that would be done. So the ratio between zinc and aqueous hydrogen chloride is a 1:2 ratio. Now, limiting reagent, excess reagent comes into play here. So we're calling limiting an excess reagent. The strategy here is calculate the number of moles of each, compare what we have to what we need. The number of moles of HCl is clearly not twice the number of moles of zinc, but it needs to be. Okay, so because of that, HCl is the limiting reagent, and that means it will be completely consumed. So we can, at this point, ignore the information related to zinc. It's in excess. Another way to look at it would be half of 0.150 is more than, is less than what we have for zinc. So the amount of zinc is exceeding the required amount to completely consume HCl. So now we can look at what's required, the amount of zinc remaining. Actually, in this case, we're going to need to come back to that amount, but here the products are not important. So I'm going to use the remaining space to work out the amount of zinc that will remain. Okay, and my last step here, having looked at the amount of HCl that was consumed, half of that amount in moles would be required of zinc, so the amount remaining for zinc would be the difference between the initial amount and the amount consumed, so multiplying that back by the molar mass to get the grams of zinc that should remain would produce a value of 1.8 grams. The last two questions on here are best just left for you to practice on your own in class. Number 2 deals with a titration, which is just a type of chemical reaction. Number 3 is a little more familiar with gas being produced, but again, volume and concentration units are there. So just to sum up for this section here, the really important consideration is that we understand all of our stoichiometric relationships very well. So go back through and review the different relationships that we've been looking at. The ideal gas law was also a relationship that we need to include in this process. So PV equals nRT. It's a formula that we'll often need to draw on whenever we're not under standard temperature and pressure or ATP conditions. And in this worksheet here, you'll just be applying this process over and over again of balance equation, converting or applying what they call conversion factors for the given substance and the one to be calculated. The conversion factor might depend on the state of matter. The amount in moles is always going to be eventually related by a mole ratio to the other reactant or product, and then finally converting back. So you're going to get lots of practice with the conversion factors that are listed here and the use of your formulas. So we'll see you in class tomorrow.